All right, so now what I want to do is kind of sum up everything that we've talked about up to this point. I showed you a little bit about how the garbage collector creates these latencies. When we're internal latencies, right? Why is my software not running as fast as it otherwise could? And we have those internal latencies around garbage collection. Also, how efficient you get data into the processor is going to matter quite a bit. And so I want to kind of sum all of that back up with getting back to talking about data semantics, our value and our pointer semantics, and start looking at code because I asked you just to start learning these mechanics, but we got to start understanding at some point when we use one over the other, and we're going to start getting there. So we're going to start off with a little bit of code here. There's some interesting things in this code that I want to share that will help us better understand how we can start engineering finally here, right? Remember a couple of things here. As we look at code, the idea is to be able to start to understand the cost of that code, right? And again, we're not going to hide that cost. It's also about, optimizing for correctness and having the guidelines around being able to do all of that. So as we start looking at all this stuff, I want you to see the sympathies we're talking about, all of these things that are going to help us be better Go developers. So if we start right here on line 14, what we're doing is we're allocating an array of 5 strings. Now, Go's not trying to be novel. You've constructed arrays before. Nothing crazy going on in line 14. But when I see line 14, because we're on the playground and a string is a 2-word data structure and each word is 4 bytes, and we've got 5 of these, we essentially have 40 bytes of values here, right? A contiguous block of 40 bytes where each one of these indexes is set to its 0 value. So this is what we have, right? These 5 strings all set to their 0 value. We're using var again for 0 value on line 14. Now, on line 15, what we're doing is we're performing an assignment operation. Now, an assignment operation is nothing more than a copy, if you really think about it. And what we have there on the right-hand side of this copy is another string named apple. So we could look at that as this. There's the bytes for the string apple, A-P-P-L-E. It's got those 5 bytes, that's apple. And if we look at that assignment, the question now becomes, what are we going to be copying? Well, what's cool is we're only going to copy the string value, Remember, string is a 2 kind of part data structure, but we know what the cost of this assignment is because it's just going to be these 2 words, right? Just these 2 words. Boom, there we are. And what I want you to notice on the 2-word copy here is the efficiencies that we're getting again from our string, or I'm sorry, from our pointer. And this is what we're going after. Let's talk about our data semantics one more time. When we talk about value semantics, what we mean is every piece of code is operating on its own copy of the data. That gives us that isolation. It helps protect us from side effects. Mutations are isolated. They're not application-wide. We love this stuff, right? Pointer semantics means that there's a single version of any given piece of data and that it's shared. And there's efficiency in sharing, but we have to worry about side effects. And what you're seeing right now is after line 15, we've copied these 2 words into these 2 words, right? We've got kind of our value semantics going on here. Here's a string, here's a string. But they both have pointers to the same backing array. Now we've got our pointer semantics coming into play. The efficiency where we get to share this. And if you look on the board so far, we've got these 3 values, right? We can isolate this for a second. The only thing that is of any unknown length at any given time will be the backing array. We know at compile time what the size of these things are, but strings can be of different sizes. So the one thing that is potentially unknown is the thing we're sharing we're going to get the efficiencies for. It's pretty cool. We're going to keep going with this idea because we're going to move over to line 22. And when we go to line 22, what we see is the for range loop. Now, a lot of Go developers, even very experienced Go developers, what they don't realize is that there's 2 flavors of the for range, but each flavor, this is what they don't realize, actually represents a different data semantic. And what you're seeing right now on line 22 is the value semantic form of the for range. Remember, value semantics means that every piece of code is operating on its own copy, and we're going to iterate and operate on our own copy. Fruit is a copy of every element that we're ranging over. Now, this would be the pointer semantic form of the for range, where we're not going to get a copy of every element. We're just going to index directly into it in that shared mode, right? But right now I'm working with my value semantic form of the for range, which means that fruit is going to be a copy of every string that we're iterating over as well, which means that on the first iteration, fruit, here it is, fruit, right, is also going to be a copy. And now if you look, I've got three string values now sharing the same backing array. 1, 2, 3. Again, getting efficiencies from that pointer semantic. But everybody can essentially here, we can have multiple copies of the string, all sharing the same backing array. Very, very, very cool. And I want you to look at one more call right after that on line 23. We have the call to print. There it is, right? The call to print. And what's happening on print? Well, we're about to move across a program boundary, but on this call to print, if you look, the print function's getting its own copy of fruit. So we can imagine now that on the frame below us, there's going to be another string value for the print call. And now I've got 4 string values all efficiently sharing this. Now, where do these efficiencies are coming from? I want you to think about this for a second. The idea of this string right now is that we leverage our value semantics. That means everybody can get their own copy of the string, right? And that means that these values here can be on their own cache lines, essentially, but in local data on our stacks. The thing that's being shared is the only thing, let's say, that would really ever have to end up on the heap. This right here, this and these cache lines here. We're going to get those efficiencies. Now, right now, that doesn't have to be on the heap. It's a constant, but normally strings are going to be a little bit more dynamic. So what's interesting here is that you're starting to see this idea that we have to balance our value and our pointer semantics, and we have to be really reasonable for the data we're working with on what semantic we're going to use, and we're going to have semantic consistency. So one of the things I can do right now is give you a good general guideline as we move forward for our data, and we can focus right now on the built-in types. And here's the initial guideline that I want to give you. And remember, there's exceptions to everything, and engineering is about knowing when to take the exception and why as well. But here's a general guideline. When we're working with the built-in types, when the data we're working with is either a numeric, a string, or a bool, what we're going to want to use is our value semantics to move that data around the program. That's going to be our guideline. That means everybody gets their own copy of the int. Everybody gets their own copy of the string. Everybody gets their own copy of the bool. We're not going to share this data across program boundaries. In fact, this data has been designed to be copied, and anytime we can use those value semantics, remember, we're going to be able to reduce allocations on the heap, which is going to help us with those lower latency costs when the GC does run. So we're going to use this guideline, right? Everybody can get their own copy of the string value, because at the end of the day, the only thing that would really have to end up on the heap would be this backing array. There's going to be efficiencies in all of this. If we were going to put everything on the heap, the garbage collector would have to manage 5 values. Right now, the way things are being designed, only 1 potential value would have to be managed. We're going to reduce those allocations by leveraging this kind of pattern. So there are exceptions. I'm going to give you one exception to this rule for a built-in type. Go doesn't have the concept of null, right? Because we have 0 value, you can't necessarily have the idea of an absence of value. In other words, you can't say because the string is empty, it's absent of a value. I mean, think of a database. What if you did a database call and there was a string for a field and it was empty in the database, it comes back empty. But what if you wanted to know if that field was even part of a select statement? You wouldn't be able to use the 0 value. We need a way of introducing the concept of null. So these are cases where a pointer of a string or an int might come in handy because you need to represent null. And by the way, when I say to you that we're going to use our value semantics to move this data around, I'm not just focused on function parameters and return parameters. I'm also talking about fields in a type. So if I saw you construct a struct type and the field was a string and it was a pointer type string, and it wasn't obvious to me you're trying to describe null, the code review is going to stop, and I'm going to say, what are we doing? We're using the wrong guideline because this is a built-in type. And it's going to be this data semantic consistency that's going to either let us win or lose this game at a micro level. We're really talking about micro level development here. So we're going to start building up some guidelines and rules for the different data that we're working with. And right now, when it comes to the built-in types, we're going to use our value semantics to move this data around the program. You saw that on line 23. We used our value semantics here to move that string value down the call stack. That function got its own string value, but the thing that we're not making copies of, what would be really expensive, is that backing array. There we're going to use our pointer semantics and gain efficiencies.